Hello, Math 126 students. Somebody's asked me about a different volume question from one of my lecture notes. And so I thought I would just go through that and use our same steps and talk through it because I like to have lots of examples here. Do watch my previous ones where I've done several of these. So this was from my lecture. This is where I am starting to explain this, one of our earlier examples. And I'll show you some visuals to go with it. So step one, find your z's. This was the first example where I showed you where we had two z's. That means you're between two surfaces. Again, in this course, we're just talking about problems where we're assuming z is the output. So these are our two surfaces. Those are the two integrands. And in doing this problem, I'll answer a few of the questions that were being asked on the discussion board. But this is what I need to compute. I need to compute that. That's going to be some volume underneath that surface. I don't know why I called it volume 2, volume 1. And this is this surface. So it's a plane. It's that plane right there. So we're going to find a volume under there. But the question is not about the volume under there. The question is about between these two surfaces. So we're going to need to also think about the double integral over some region of 1 dA. And we talked about those, so let's call that volume 2 right here so you can see it. So that's volume 2, and over here is volume 1. So conceptually, you don't have to really think about that. It's just we know now there are two surfaces to work with, two different heights, so to speak, and we're going to have to figure out how to put them together at the end of the problem. Now, that other surface is just a plane like this. Now, a lot of times students go, well, how would I know which one's on top? You don't have to know yet when you're doing the problem. We can see which is on top now because I've shown you this picture. But I still just move on to the next step. We can come back to that in just a moment. So the next thing we do is we draw the region. So you do an XY plane and you draw. There were two steps. Are there any given XY equations? Because it says first octant, we are assuming the other equations we have are x is greater than or equal to 0, y is greater than or equal to 0. So those are those sides. So you have a side, and we're inside here. So the reason I'm not drawing the entire circle is because we're in the first quadrant. So it is saying above this region on the ground. Okay, so you don't need to know the surface for this. You do need to know what the region on the ground is. Oops, that's not it. Let me draw it here. There's the region on the ground. We just figured it out. If you wanted to know which surface was higher, you could, even though you don't need to, you could pick a random point in the region. For me, I would pick 0, 0. So you say, well, if x is 0 and y is 0, and I consider the two surfaces, 1/3 y, and z equals 1, which one is bigger? Well, if you put in a 0 there, a 0 is smaller than 1. So you can see, so I know just from doing that, which one's going to be bigger. This one will be bigger because 1 is bigger than 0. You could plug in a few other values if you wanted to see, but that's how you do it without even having to look at it. So going back to the surfaces, here they are. 1 is bigger than this over that entire region, and they don't intersect at all. Usually the other step we do is we ask when do they intersect, but these two things intersect when y is 3, which is beyond our region. You can't see it even. It goes out past. I would have to graph it further for you to see it, but that's not above our region. And we really don't want to look at the entire surface. We only want to look at the part of the surface that's above there. So we're actually only looking at that. So we're going to find the volume up to there, which actually we could do without calculus. And then we're going to find the volume up to, let's see if I have it here. Not that one. Oops. I'm using a different system than I usually use here. These are just different sides of it. I keep clicking the wrong ones. There it is. Okay, there we go. So I'm doing the volume between those two. Okay. I didn't need to see any of that to do this problem. I just had to move forward. Now, the preferred method for me, if I was doing this, would be polar, because then I could just say the bounds are from. So, if you, a small comment before I move past what I just said, you could put the two integrals together. There's not an advantage or disadvantage to doing it, meaning you could either compute them separate and then subtract, or you could compute them together and do the subtraction as part of the calculation. Both are fine. And as I said, in this case, there's not a real advantage to one over the other. If we want to do them together, then you would say 0 to pi over 2. That's the angles we're talking about. And 0 to 2, 1 minus 1/3 y. Oh, not y, I switched to polar. 1 minus 1/3 r sine of theta. And then I would put, this is a disadvantage of putting them together, I would put parentheses here because you then need to do r d theta. And you need to multiply that whole thing. So at that point, then we're just computing. If we wanted to, we could have computed them separately. That also would be fine. And then subtracted, or you can compute them together. If you compute them together, then you're going to distribute and just keep going with your calculation. So this is going to be the integral from 0 to 2. It's going to be r minus 1/3 r squared sine of theta dr d theta. And now we can integrate the r's. Maybe I'll scroll this up a little bit. Let's get a different color. So now we're just switching to computation. But I hope we've answered that question. But let's go a little further here. 1/2 r squared minus 1/9 r cubed sine of theta. R goes from 0 to 2 d theta. And then you plug this in. 0 to pi over 2. Plugging in a 2, you're going to get 2 squared over 2, which is just 2. And here you're going to get 8 over 9. These numbers are starting to sound familiar to me. Let's scroll up a little more. So then we finish. We do this last integral. So it's going to be 2 theta. It's going to be plus because it's going to be the antiderivative of sine is negative cosine. So I guess that's kind of nice. 0 to pi over 2. Got to be a little careful when you plug these numbers in. Pi over 2 plus 0. That's what you get when you plug in the pi over 2. Minus 0 plus 8/9. I think that's what I said the answer was. In one of the classes I said the answer. I think in the other class I didn't quite finish. That's that volume. So that's pi. It's a little, pi is 3. That's a little, so it's a little more than 2 is the volume of that. And what we just found, not that, we found the volume between all these things. So I have it set up so I can show you the other sides. I keep clicking the wrong thing. That's the that's the ground. That's fine. We're doing this, and then we have one other side there. So we're finding that volume. You know, one thing you can always do is ballpark it. You know, it's 2 by the area on the ground, I think, is pi. Yeah, because it's 1/4 of pi r squared. And then the height is 1. So it definitely should be smaller than pi. How much smaller you could sort of ballpark geometrically. Anyways, hope that answers that question.